Hi everyone, I am Xinzi Li. I received my PhD degree from Nanyang Technological University in Singapore with an interdisciplinary background bridging power electronics and artificial intelligence. I am currently a postdoctoral researcher and lecturer at the University of Arkansas. In this first video, we will explore the future of AI-driven automation in power electronics design, using a flyback converter as our example. I have prepared a small hands-on exercise where you will design a coupled inductor using generative AI. Give it a try and see what insights you can uncover. I will also give you a quick overview of the upcoming episodes in this AI for Power Electronics series. Stay tuned, and I look forward to having you join us.
Today, we are diving into a rapidly evolving frontier, artificial intelligence in power electronics design. Whether you are new to AI or new to power electronics, this series will guide you through key concepts and hands-on experiments. And more importantly, it will help you see how AI is becoming a trusted core designer in the next era of power electronics innovations. Before we dive deeper, here's a quick look at what this journey holds. This isn't just a one-time talk, it's the beginning of a series dedicated to empower you as an AI-driven power electronics engineer. In the episode ahead, you will learn how meta-heuristic algorithms can solve converter optimization more effectively in multi-objective ways, how machine learning characterizes converter behaviors, and how reinforcement learning serves as the next generation adaptive controller. We have also covered cutting-edge physics-informed machine learning for multi-physics modeling, and get ready for the showstopper, generative AI that transforms your specs into feasible designs through natural language prompts. By the way, I'm not alone on this journey. We have featured leading voices in the field: Dr. Mingji Chen on magnetic modeling, Dr. Adam Mentos on power module design, and Dr. Peter Wilson on design automation. So, a big shout out to stay tuned with us. Let's step into the shoes of a power electronics engineer. We have been asked to design a flyback converter. The first step is to understand its operating principle. During T-on, the MOSFET turns on, and the energy builds up in the magnetic field of the coupled inductor. During T-off, the MOSFET switches off, and the diode conducts, and the stored energy is converted to the output. So far, everything sounds straightforward, until we realize how many variables we have to deal with, including the selection of the switching devices based on the current stress, voltage stress evaluation, detailed coupled inductor design, including the core selection, its geometry, the inductance, the windings, etc., rectifier diode selection, and output capacitor bank design, and there are many other important parameters like switching frequency, etc. Then what about the operating performances? Shall we prioritize efficiency, power density, reliability, or cost? These performances themselves are conflicting with each other. Taking any component has non-trivial impacts on the entire system. This is exactly where the real challenge is. The design space is nonlinear, multidimensional, and deeply interconnected. For decades, engineers tackled this complexity manually, running loop after loop of spreadsheets, simulations, and empirical experiences. Here's what flyback converter design actually looks like for most engineers today: a very human-centric, step-by-step design process. Structured? Yes. Efficient? Not always. We begin by inputting basic specs like the voltage or efficiency requirements, etc. Then here comes the math, calculating the inductance, turn ratio, MOSFET, and diode stresses, etc., based on which the components are then selected. Each step depends on the last. Each decision we make could affect system efficiency, compactness, etc. So, naturally, what happens next? That's right, we iterate. Once, twice, 99 times if needed. Well, the kitty might be crying by then, and every loop means tweaking the models, running a simulation, reading the datasheets, and often chasing our tails. This is where AI steps in, not to replace engineers, but to free us from these endless loops and elevate our role to system architects. Now, here's where things get exciting. What if we could just chat your way through the power converter design. So buckle up because we are shifting gears into a generative AI driven design paradigm that potentially elevates how we actually engineer in the future. Well, with PE-GPT, we are no longer stuck in implementing spreadsheets manually. Instead, you simply describe your design requirements in natural language as if you are chatting with a colleague. The AI takes your request in natural language and launches into action, handling multiple tasks that you define, including the modeling, perimeter design, component selection, simulation validation, and even virtual prototyping, or from your text prompts. It can generate full design details from initial design specifications to validated simulations, all the way to ready to prototype virtual hardware assemblies. While AI does the heavy lifting, you still remain in the driver's seat, guiding, validating, and fine-tuning results. Your effort will be spent on engineering insight, not endless iteration. Again, this isn't just a productivity boost, it's a paradigm shift. Say hello to a future where engineers and AI co-design together, unlocking a new era of fast cycle, intelligent, and creative power converter design. Let's look at a quick design demo to use PE-GPT for flyback converter design. To start, PE-GPT will recommend you a converter topology based on your target applications. Here, we are designing the power supply for a single board computer like Raspberry Pi. It suggests a flyback converter and explains from several aspects such as efficiency, galvanic isolation, and more. Once the user confirms, the PE-GPT asks for additional information to design it, including the key expectations like the efficiency requirements, voltage ripple constraint, etc. With these details inputted, it generates the complete design and summarizes the key parameters into the flyback converter circuit diagram. Key waveforms, as we can see later, such as the inductor current, output voltage, have been evaluated. PE-GPT also produces a detailed report, which outlines the design process step by step. Afterwards, the design can be verified seamlessly with a simulation tool without any additional configuration by the user. Here comes the next step, component selection. The user wants to select MOSFET switches for that design. You can either provide your custom database or use the default one. With the database provided, PE-GPT plots blue dots for components that match the evaluated voltage and current stresses. The user can also customize the view by selecting different objective axes. The global optimal solutions are plotted by the red Pareto frontier. You can click on it to take a deeper look into the selected component. Other than the manual selection, the PE-GPT also provides an intelligent engine to provide recommendation. For example, the user wants a chip component with high efficiency. It picks some components that meet your criteria. Click the link provided. It will direct you to the datasheet for more details. Alright, I know many of you are eager to try out the generative AI to help your converter design. So let's take the coupled inductor design for the flyback converter as an example. Just scan the QR code here or head straight to ChatGPT's homepage. Then copy the prompt you see here, paste it in, and hit enter. Do note that the flyback parameters listed here are generated by the PE-GPT, providing the ChatGPT all the context it needs. Let me show you how it works. So we will be directed to the homepage of the ChatGPT, and then we are going to paste our design specifications generated by the PE-GPT. And then let's press enter and see what the design the ChatGPT provides for us. After pasting the prompt, the ChatGPT returned, I would say, a quite complete coupled inductor design, including the core type, winding configurations, shape, material, and even, if we are lucky enough, we will see a suggested part number. If you are not satisfied, you can just tell it. You can simply iterate your design through conversation. This is exactly what generative AI powered design actually feels like. It feels like interactive, fast, and surprisingly intuitive. So, go ahead, give it a shot, and who knows? This simple experiment might just spark your next breakthrough in AI driven power electronics design. Oh, so with artificial intelligence, well, it leads us towards autonomous power converter design. At the base, we had conventional manual design or PE design 1.0. Then computer-aided design tools appeared. Well, PE Design 2.0 introduced simulation and CAD tools, helping us to analyze the behaviors and accelerate prototyping, yet still keeping engineers fully in the process. Today's cutting-edge industry practices have reached PE Design 2.5, where advanced meta-heuristic algorithms are used for multi-objective converter optimization. In research, we have stepped into the AI augmented design (PE Design 3.0). Tools powered by machine learning and meta-heuristic algorithms can now learn from data, automatically build accurate behavioral models, systematically optimize across the core design variables towards high-performance power converters. And what's the next generation of power converter design? Well, P Design 4.0 autonomous design, where detailed converter design specs can be automatically generated with minimum or even without human supervision from just a high-level prompt. While PE-GPT is not yet fully autonomous, its generative AI-assisted nature paves the road towards PE Design 4.0. This AI evolution unlocks real challenges: faster time to market, automation of tedious tasks, code design across domains, and a lower barrier for entry. They provide anytime generic intelligence, empowering not just experts, but learners, startups, and multidisciplinary teams. And remember, AI won't replace engineers, but those who know AI will. So the best time to learn about AI in power electronics is now. We have now seen what's possible with AI in power converter design, but this was just the tip of an iceberg. A big shout out again to the episodes of AI in power electronics design. Now, don't worry if these terms sound unfamiliar. You don't need a machine learning background to follow along. We will walk you through in our next intro video. Now, let's take a closer look at the first two episodes in the series. This will lay the technical foundation for everything that follows. First, we will explore nature-inspired optimization techniques, meta-heuristic algorithms, such as the particle swarm optimization algorithm shown here. You will learn how they help us search complex design spaces, balance multiple performance objectives like cost, power density, and efficiency, and construct parallel fronts for multiple objectives trade-offs and find globally optimal solutions. Next, we will look at machine learning for converter modeling. The idea here is to replace traditional modeling with data-driven machine learning models. For example, instead of running electromagnetic thermal finite element analysis to analyze the maximum junction temperature of different power module layouts, we will use a neural network to learn from the data. This figure shows the training process of an example learning algorithm for the efficiency modeling of a buck converter. This is a separate case study. Here comes more advanced topics. We will explore how reinforcement learning can be trained to control power converters by a trial-reward learn way. Think of it as a neural network that replaces your PI controller, your model predictive controller, your MPBT controller, etc., or your modulators. In addition, we will explore physics-informed machine learning, which serves as the next generation AI for power electronics. It can integrate power electronic physical laws into the model learning process for physically accurate and faster multiphysics modeling. Finally, we will dive into how generative AI like PE-GPT can elevate power electronics design automation, all from simple text prompts. We are excited to have top experts who are pioneering the fusion of AI and PE engineering. Magnetic components like transformers and inductors are often the bottlenecks in converter design. Dr. Mingjie Chen will show how AI can model nonlinear magnetic behavior, capturing core hysteresis and saturation effects from real-world data with high accuracy. Dr. Elementos will dive into AI-driven layout optimization for power modules. You will see how machine learning and Pareto optimization can reshape 2D, 2.5D, and even 3D power module layouts, balancing the parasitic inductance, reliability, thermal resistance, and more. And we are just getting started. As we build momentum in this series, expect more cutting-edge applications and guest insights to come. We are standing at the edge of a new era, where artificial intelligence empowers power electronics engineers to build faster, design smarter, and innovate like never before. As Stephen Hawking once said, intelligence is the ability to adapt to change. And in this new landscape, adaptation means embracing AI, not just as a tool, but as a collaborator. So, whether you are a student, researcher, or industry professional, now is the time to take the step and elevate your capabilities. Thank you for joining this introduction. I am Shinzi Li from the University of Arkansas. Stay tuned for our upcoming episodes, and we will help you become fluent in this new design language. Hello world, hello power electronics. Let's design a future together.